Make sure I record these because I changed the lessons for the first time in a while. We're talking about electric field. First of all, let's talk about gravitational field. The way that an object like the Earth is able to exert a force, a gravitational force, from a distance is that it is touching it in the same way as I was able to use a meter stick to poke Ruby from a distance. It's just that the Earth is touching it with something that you can't see. The gravitational field reflects the effect that mass has on the space around it. So this planet, let's call it the Earth, is sending out, like the invisible tentacles of an octopus in all directions, a gravitational field. That is always there. If you wanted me to assign a direction, it would be, you can put arrows pointing towards the planet because that's going to be the direction of the force. That gravitational field, Dean, will sit there passively until a wandering mass enters that gravitational field. Oh, what's our symbol for gravitational field? Little g. Earth's on the surface is 9.8, but if you want to calculate it anywhere, it's big G, big M over R squared. When does it become a force? Well, last year when I said get the obvious one, what did I always mean in Physics 11? What? What did we write in our free body diagram? 2 letters. And that's where Newton's universal law of gravitation came from. So as soon as this little m ends up in the gravitational field, it will now experience a gravitational force. By the way, so will big M because forces come in pairs, but we're just focusing on that small object. So example 1 says, fill in the appropriate relationships. The force of universal gravity was big G, big M, little m over R squared. We defined gravitational field as the gravitational force per kilogram which means if I take it one step further as an equation, when the little m cancels, it was that. What were the units for gravitational field? It comes from the definition. What do I measure force in? What do I measure mass in? Which one of these 2 versions did I use? Well, it depended. If they gave me the mass of the little satellite or object, and if they gave me the force it was feeling, I could find the gravitational field. If they told me the mass of the object creating the gravitational field and how far I was from its center, I would use that. Basically, if they gave me meters, I would use the one that had meters in it. If they didn't, if they gave me newtons, I would use the one that had newtons in it. Kyle, what does part A want me to find for example 2? What does part B want me to find for example 2? Ha! I'll bet you will use one of each. I'm going to draw a little line down the middle of the page. Here's part A. Here's part B. You know what? The fact that they gave me a distance, I think I'm going to use the one with the R with the radius in it. I guess Earth is going to be big M, and so I can find the gravitational field strength by going big G, big M over R squared. Big G was 6.67 times 10 to negative 11. Mass of the Earth, what, 5.98 times 10 to the 24th, I think? All over. Do I need to add the radius of the Earth, or is this 8.3 times 10 to the 6th already measured from the center of the Earth? Oh, so I don't need to add to it. It's just going to be 8.38 times 10 to the 6th. Don't forget the squared. I know the answer is going to be less than 9.8, but it's not going to be 0. What do you get? You back with me, Marcus? Okay. Because you were elsewhere for a bit there. Okay, what'd you get? Yeah. 5.68? Sure. Newtons per kilogram. Also, technically, you could think of it as meters per second squared because it's also an acceleration. But what did you say part B wants me to find? Okay, now I notice they gave me the test mass. That's the object in space, and they gave me its weight. They gave me the gravitational force. Now I would find little g by saying it's going to be the force of gravity on that mass divided by that mass. So what's the force of gravity? 750 newtons. What's the mass? 10. I don't know where we are in space, but apparently at this location, whatever mystery planet we're orbiting, not Earth, the gravitational field strength there is 75 newtons per kilogram. Maybe we're near the sun. I don't know. What I want you to realize is gravitational field is what's actually grabbing and exerting the force on that other object. It is not actually at a distance, it's just invisible. And there's two ways to calculate it. We're going to define electric field in a similar manner. The electric field reflects the effect that charge has on the space around it. So here is a big Q charge. It's sending out, like the invisible tentacles of an octopus in all directions, an electric field. Our variable for electric field is going to be a capital letter E with a vector sign above it. In fact, we'll often talk about an E field. That's an electric field. Bit of a problem here. For gravitational field, I drew the arrows in down because gravity always pulls towards itself. But Joanna, like charges, what direction are the arrows here? It depends. We're actually going to have to define the direction of electric field. That's going to be a bit later on in this lesson. But the reason we have to define a direction is, unlike gravity, like charges repel. So what happens is, if another charge is placed in that field, it will feel either an attractive or repulsive, I'm not sure which, force, an electric force. In the same way as if a satellite wanders into Earth's gravitational field, or if an asteroid wanders into the sun's gravitational field, it will feel a gravitational force. Fill in the appropriate relationships. So we have the force of electricity, which was K, big Q, little q, over r squared. The definition of electric field, if the definition of gravitational field was gravitational force per kilogram, the definition of electric field is electric force per coulomb per charge, which gives us our first equation for electric field. The electric field, if you know the electric force that a charge is experiencing and you know how big that charge is, that will let you calculate the electric field. What would the units be for electric field? What are the units for force? Brandon, what are the units for charge? Newtons per coulomb. Newtons per kilogram, gravitational field. Newtons per coulomb, electric field. Okay. I wrote here, it's a scalar equation. I know I put vector signs on here. The equation itself just tells you the magnitude. We're going to have to figure out the direction by defining a direction in a little bit. Or we can also find the electric field if we know the planetary charge that's creating the field. You know what? It's going to be this equation canceling out the little q. See it right from here? It's going to be K big Q over R squared. When would I use either of these if they ask for the electric field? Oh, I would use the bottom one if they also gave me a distance in meters. I would use the top one if they gave me a force in newtons. They're going to give me coulombs. Can you all look at your formulas pages, please? And we're actually going to write on the yellow sheet. So you want your yellow sheet out as well as your blue sheet out. So the section we're looking at right now is electrostatics, but you can all, because I'm skipping this year, draw a line through that little section like that, both on your yellow and on your blue sheet. Hope it doesn't come back to bite me. No. Oh, by the way, did I give you both versions of electric field on your formula sheet? Yeah, I didn't do it with gravity on purpose. I thought about it, but I really wanted to reinforce that field is force divided by mass for gravity. Field for electric field is force divided by charge. Oh, what did you say the units were, Brandon? I'm not sure what you're referring. Newtons per coulomb. By the way, in the same way that gravitational field is newtons per kilogram or meters per second squared, there's another way to measure electric field. It's volts per meter, but we're going to skip that this year. Yeah, turn the page. Uh, as was the case for electric force, electric fields cannot be negative, and so we don't put a negative in if the charge is negative. That's why there's absolute value signs on your formula sheet. Okay. Hannah, in example 4A, what are they asking me to find the magnitude of? In sorry? What are they asking me to find the magnitude of in part B? Oh, are these the same question? You know what? We have two ways to find electric field. I'll write them both here because you've all turned the page. One way to find the electric field was just its definition, which was right from the units, newtons per coulomb. But another way to find electric field was if you knew the planetary size charge that was creating the electric field. Really, if there was an R, if there was a meters, I would use that one. Which one am I going to use for part A? The first equation, what we call the ratio definition, or the typing in the stuff? So now look at the data that they gave you. What's the units next to this 5.2 times 10 to the negative fourth? Which one of these has force in newtons? Apparently, the electric field is going to be the electric force. And there's a bit of a problem here. Can you see it would be really easy to confuse force and field? They both start with F, and all I can say is please don't. A few of you on the test confused, I think maybe it was you too, gravitational field with gravitational force on the black hole question. We'll go through it. And unfortunately, I had to give you a 0 on that section because I couldn't give you part marks. You found the wrong thing. What's the electric force this charge is feeling? What's the charge? Are we going to put the negative in? No, absolute value sign. 0.5 and ooh, Taya, this was new as well. Jaya, this was new as well. What was that little micro coulombs? What was micro? 10 to the. This one's worth memorizing during this unit, but 10 to the top left. There's the chart. 10 to the. Yes. Were you way overcomplicating? What you know? Okay. What do you get? I do this in my head. 5.2 divided by 0.5 is going to be 10.4. Now, what about the power of 10? 10.4 to the negative 4, 1040, he says, guessing. Double check me. Yeah. Units, Brandon? Okay. Typically, electric fields will be in the thousands. Actually, usually they'll be in the tens of thousands or hundreds of thousands of newtons per coulomb. Hannah, what does B want me to find? Didn't we just find that? Ooh, now I notice they gave me a distance, and this is the charge that's creating the field. So now I'm going to go K big Q over R squared. It's going to be, what was K again? A nice constant. What was K again, folks? 9 times 10 to the ninth. Pause for 1 second. Ooh, what's Q? Uh, 2.3. Hannah, what does micro stand for? 10 to the? Yep. All over 0.45. Don't forget the squared. And in both of these, I just asked for the magnitude. The reason is I haven't yet taught you how to find the direction. Marcus, let me know what you get. What'd you get? 102,000? And probably some decimals or not? Newtons per coulomb. By the way, that means 1 coulomb of charge would feel 102,000 newtons of force there. This is also why I said to you yesterday, 1 coulomb of charge is massive, huge. Lightning bolt would probably have anywhere from 10 to 25 coulombs of charge. So you're already talking in the lightning bolt range. The direction of electric field. With gravity, this was never an issue because stuff always fell towards each other. But with electric fields, with charges, like charges, so we have to define it. This part you'll need to memorize. You can add it to your blue sheet. You can't add it to your yellow sheet. The direction of the electric field, here's what we do. We say, where are we talking about? Oh, right there? Okay. We imagine a tiny positive charge sitting at that location, and we ask, what direction would a positive sitting there want to move if it could? It's the direction a small imaginary positive test charge would go if placed at that location. Petra, there's a shorter version. I've seen some textbooks say it's from positive to negative. The problem is sometimes in your diagram, you won't have a clear positive or negative in your picture, but if you can imagine a positive charge at that location, and it's an imaginary charge, it's really tiny. How tiny, Eric? So tiny it doesn't have its own electric field because that would change the question. But it's positive. Oh, calculus students, it's a limit. So example 5, the question that Hannah and I just did, it says, find the direction of the electric field at a point where a negative charge experiences a force toward the south. So if everybody can underline the charge, it's negative and south. If a negative charge is feeling a force to the south, which way would a positive charge feel a force? The electric field direction is north. Oh, the magnitude we calculated, that was the 1040 previous question. B, now I've given you the picture. So we are to the right, we're sitting right there. The charge that's sitting right there, oh, we're not going to actually look at this. We're going to imagine a tiny, tiny, tiny little positive right there. What's the charge on big Q? The question told me. Is the charge on big Q negative or positive? Aiden, see it? So everybody put a big plus sign there. Which way would a little positive at location X want to move if it could? Would it be attracted to the left or repelled to the right? What direction is the electric field? Same answer. Michael Faraday popularized, first of all, he came up with and coined the term fields, and he came up with the idea of lines as pictures. So it says, draw the electric field around a positive charge. Do me a favor, all of you, draw a little line like that, a line like that, a line like that, and a line like that on the 4 points of the compass. We're going to put arrows on these lines. Which way will the arrows point? On this top line, imagine a little positive test charge sitting right there. Which way would that positive want to move if it could? Up, away, repelled, or down towards attracted? What about this right here? What about this? What about that? There will be a multiple choice question on your test where I give you a picture of electric field lines, but I don't tell you the charge. And I ask you to tell me, hey, negative or positive? Two negatives, two positives, one negative, what? I'll give you two charges and I'll show how they're interacting. So electric field lines show us the direction. Also, they show us the relative magnitude. If I had another charge with 8 lines, I would assume that that charge was twice as big as this charge. Doesn't mean it's 2 coulombs and 1 coulomb. It just tells me it's twice as. Oh, if there was another charge with 12 lines, I could say, okay, that charge is 3 times bigger. Some other phenomena with electric field lines. The closer the lines are, the stronger the field. The further the lines are, the weaker the field. In other words, the distance between these here is smaller than the distance between right there. Stronger field right there, weaker field right there, which works out from the R squared in the equation. Draw the electric field around a negative charge. Okay. I'm going to make this negative charge twice as big as the positive. I'm going to draw 8 lines. On any of those lines, what's the direction of the electric field? Well, on any of those lines, which way would a positive want to move if it could? Repelled away or attracted toward? So the direction of the electric field, we ask, which way would a positive charge at that location want to move if it could? That's how we decided to define it. We could have defined it in terms of negative charges. We defined it in terms of positive charges. And the reason we had to define it is because unlike gravity, where everything is attracted, in electricity, Joanna, like charges repel. This brings us to the electric field of dreams. I just added a charge. Look at the electric field lines. Is that charge positive or negative? And how do I know? How do you know? Because a positive nearby would want to move towards it. Okay, I'm going to add another charge. They're going to exert forces on each other. And so as they exert forces on each other, they're going to repel each other. Now what I'm going to do is I'm going to change the property. Instead of adding a negative 1 coulomb charge, I'm going to add a positive charge. Add. One of those charges is positive. 2 of them are negative. Pause. This charge right here, negative or positive, how do you know? How do you know? Electric field lines are pointing away from it. A positive would be repelled. This charge right here, electric field lines are pointing towards it. This charge right here, negative, electric field lines are pointing towards it. Now there's 3 positives and 2 negatives. This little kinetic dance is going on at the molecular level all the time. Positives and negatives, all interacting with each other. This is what helps contribute to what we call Brownian motion. So if I freeze it, how about right now? This charge right here, positive or negative? How do you know? Pardon me? Which one, positive or negative? How do you know? Oh, because positives would want to move towards. What about this one? What about this one? This one, positive. This one, negative. Okay? Set. I'm going to tell you right now, example 6, will you marry me? Okay. There's going to be a question like this on your test. I'm going to ask you to find the overlapping electric field between 2 charges. Arian, just pick up where we are right now. We also made some changes to the formula sheets, even to the yellow one, so make sure you ask Fahim for that one later. We want to find the overlapping electric field between two charges. To do that, we use something that we fancily call the principle of superposition. It just says, look, do them one at a time and then add them vectorially. So example 6 says, find the electric field, magnitude, and direction at that point. Is there more than one charge in this question? Who remembers what I said you should do anytime there's more than one charge? Yesterday I told you first thing you should do is what? Just to do yourself a favor. Label the charges. If I ever see you answering something like this and you haven't gone, hey, Q1, hey, Q2, or QL for left, QR for, I usually just use 1 and 2. Do that because now we have a common vocabulary. What I'm going to find is the electric field from charge 1, magnitude and direction. I'm going to find the electric field from charge 2, magnitude and direction. And then I'll add them vectorially. Because they're in a line with each other, it's either going to be winner plus winner or winner minus loser. I won't need to go tip to tail. I used to also do tip to tail questions. That's one of the topics I've pulled out of this shorter version of electrostatics. Okay. Ooh, which version of electric field am I going to use? Hannah, coming back at you. Which version of the electric field equation am I going to use? How do you know? That, and yeah, and these are the planetary size charges that are creating the electric fields. So the first one is going to be KQ1 over, I'll call it R1 squared. The second one is going to be KQ2 over, I'll call it R2 squared, just so I don't accidentally mix up the R's. All right. Nicole, what's K? Pause the video for 1 second. Q1, positive. Oh, I don't care about positive or negative. What's the magnitude of Q1? 1 and then microcoulomb. These diagrams were typed in Word 1995 for Mac, and I know they're dying, but I desperately don't want to have to retype all these. I may have to, but you're going to see those Mews are looking a little funky sometimes. Over, Nicole, what's R1? Oh, that's beauty. Squared. In fact, I think I can do this in my head because Nicole, it's technically 9 times 1 divided by 1 squared. It's going to be 9. I just need to do the powers of 10, and I can use my exponent rules. It's going to be 10 to the 9th times 10 to the negative 6. You just add the exponents. I think you're going to get, double check me, folks, you get 9,000 even? No, yes, newtons per coulomb. Direction, this is the key. So Nicole, which way would a positive sitting at the field point want to move because of Q1? Would it be attracted left or repelled right? Victor, I told the kids I like this question. This question is going to be on your test. Okay. Ashley, what's K? How big is Q2? Conveniently also 1 microcoulomb. What's R2? Don't say 4. Thank you. That's one that drives me crazy. The number of, oh, it's 4. No. Look where we are. Look at the field point. 3 squared. You can backspace and edit, but I think this also works out. I think it works out to 1,000. Yes. Newtons per coulomb. Ashley, direction. Which way would a positive at that field point want to move because of Q2? Would it be attracted right or repelled left? Eric, how would I add 9,000 right and 1,000 left? Am I going to go 9,000 plus 1,000, or am I going to go 9,000 minus 1,000? Winner minus loser. In your homework, if you went straight to the answer, I'm fine with that. In our notes, let's write that we went 9,000 minus 1,000, 8,000 newtons per coulomb. Direction, Eric? Right, right, right. You're going to see, by the way, I can ask you to find the electric field in between the two charges or off to the left or off to the right. It's all the same. I'll give you enough distances that you can figure out the different radii, and they'll be in a nice straight line with each other. So you'll go winner minus loser or winner plus winner. You're going to see on the ultimate review that I gave you, probably half the questions just about in the electric review, the first part, are finding overlapping electric fields. That's a hint. Yeah, we're good for time. Example 7 says, I think we're good for time. Good, 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 good. Yeah, we're good for time. Because I also got to show you Harry Potter. Draw approximately the resultant electric field at the indicated field points. Assume both charges are positive 1 millicoulomb, microcoulomb charges. They're both positive. I'm going to start right here in the middle. Which way would a positive field of force want to move? Oh, Mr. Dueck, is there more than one charge in this question? Then what should I do? Q1, Q2. Okay, so if I put a little positive right here, which way would Q1 exert an electric field? Which way would a positive want to move? Which way would a positive want to move because of Q2? And I think because they're the same distance and the same magnitude, when I typed in KQ over R squared, I'd get the same answer. I think I would get this plus, don't write that, because really, what's the same magnitude left plus the same magnitude right actually? What's the net electric field right there? Yeah. What about right here? Well, don't write this down, look up. There would be a big electric field to the right from Q1, a smaller electric field to the left from Q2. Why smaller? R is bigger. So what's the net electric field right there? But not as big. To the right, but not quite as big. So you can draw a little arrow like that. What about on the right-hand side over here? I think we can make the same argument. The net field right there would be that way. Ooh, what about up here in the middle? Well, which way would a positive want to move because of Q1? Don't write this down, just watch. That way, yes? Which way would a positive want to move because of Q2? How would I add those two vectors together? Draw them. You know what the net electric field is? I think straight up. That you can draw in. I think the left-right sections would cancel out, but Emily, there would still be a section pushing it straight up. Ooh, what about right over here? Well, it would be getting pushed straight up by Q1. It would be getting pushed a little bit sideways by Q2. I think if we draw these tip to tail, we'd have almost but not quite straight up, a little bit pointy to the left. A sim for this, I'm pretty sure, Mr. Dueck. Where is my sim? Yeah, charges and fields. So here's a positive. Here's another positive. Do those direction vectors look like what we drew? Right in the middle, there it cancels. Oh, we can even put some values on there, I think. Can we, Mr. Dueck? No, it doesn't put values on there. I think, oh yeah, sensors. Here's my electric field sensor. Right here, which way is the net electric field? Pointing to the left, is that what we drew? What did we say over here? Pointing to the right? Let's get rid of the electric field so you can see. But then we did say there was going to be a spot right near the center, right about here, where the net field was what? 0. Taya, going to make it? What was the net field up here? We said it was pointing up. And we said the net field right here would be up but a little bit to the left. That works. Draw the electric field pattern for equal like charges. Okay. So it would look something like this. One line would head out this way, but it get repelled and head up. Another line would head out this way and get repelled and head up. Line would head out this way and get repelled that way. Get repelled that way. Repelled this 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 way. I put 5 lines on each because they said they were equal. I could have added more, but as long as I had the same number of lines for each. I'll come back to this drawing in a second, but what it should look like for equal charges is something like figure 5.12, something like that, with more lines if you stick them in. And what you can see is in the middle, Eric, there's kind of a neutral zone right there where the net electric field is 0 or really, really close to 0. Up here, both positives will get repelled up, get repelled down. But basically, a tiny positive charge would follow that line if it was free to move. What about for equal and opposite charges? Well, definitely one line, jump straight across, baby. A line might leave here, straight across, kind of curved and down. Like that. There might be a line that might leave the page there, but it would come back in here. It would curve off the page and come back in. It would eventually make its way towards that negative because like charges repel and like charges attract. There might be a line that left there and would eventually come squeaking back in. If you want to see a better rendering of what 2 unlike charges would look like, figure 1.2a. On your test, I'm going to give you something like this. Or something like this. And I'll ask you to tell me, is the left charge negative or positive? Is the right charge negative or positive? How will you figure that out? Look at the arrows. Which way will the positive want to? Electric field lines point from positive to negative. So the notion of field lines comes to us, and the notion of electric field, from Michael Faraday. Michael Faraday is one of my nerd heroes. Put your pencils down for a second. Pause the video for a second. We'll come back to some Michael Faraday when we look at magnets. So he used lines of force. He drew pictures. There's mathematics for this as well. It's lovely. It's calculus that was beyond him. So you know what? Here's our picture. How many lines does this positive charge have emanating from it? 8. How many lines does this negative charge have emanating from it? 8. They're the same magnitude. I'm not saying they're 8 coulombs. They're the same magnitude. Oh, and the closer the lines, the stronger the field. The further the lines apart, the weaker the field, which ties in with KQ over R squared. So these are electric field lines. We'll do one more. Example 9. If Q1, I got time? Yeah. You got a day off tomorrow. If Q1 is 12 microcoulombs, Q2 is 8, and Q3 is 15, find the electric field right there. I'm not going to give you a 3-charge system on your test, so if you can handle a 3-charge system, you're in good shape. What are we going to do? We're going to find the electric field from Q1, magnitude and direction. It's going to be KQ1 over R1 squared. Marcus, what's K? How big is Q1? 12 microcoulombs, the question said. 12 times 10 to the negative 6. How big is R1? Don't say 0.75. Don't say 0.8. How big is R1? That would be this distance right here. More specific as a number exactly? What I'm saying is, do the math. What's R1? 1.55? Don't forget the squared. What do you get? Okay, 9 times 10 to the 9th times 12 microcoulombs divided by 1.55 squared. The magnitude of the electric field, I get 44,953, and since I'm not done, I won't round off. I'll just write that. Is that right? 44,953? No, yes? Yep. That's newtons per coulomb. Direction. Which way would a positive want to move because of Q1? Would it get attracted left or repelled right? Good. Now we're going to find the electric field from charge 2. That's going to be KQ2 over R2 squared. I've got to scroll up, Ari, and you're going to have to tell me what was K? On your formula sheet, it's that constant. Yeah. That one's probably worth memorizing, and I'm going to argue it's pretty easy to 9. What was Q2? I've scrolled down, but the question should tell you. 8 what? Microcoulombs? 10 to the negative 6 divided by, okay, what's R2? How far is Q2 from our field point? Oh, 0.8. We don't have to do any math there? Okay. Don't forget the squared. You're going to find for a lot of these, you can backspace and edit and just tweak the numbers. So instead of a 12, I'm going to make it a 0.8. That'll work as an 8. And it's going to be 0.80 there. I kept the extra zeros because I have a feeling I might want the extra decimals for the next question sitting there anyway. 112,500? Direction. Which way would a positive sitting at the field point want to move because of Q2? Would it get pulled to the right or pulled to the left? Push to the right? I agree. Is that okay, Ella? I saw some hurried whisper. Typo? Squared? Well, Ella, there's only one way to redeem yourself. Get back on the horse. So the third one's going to be KQ3 over R3 squared. 9 times 10 to the 9th. Ella, I've scrolled down. What was Q3? 15 microcoulombs? What was R3? Well, is it 1? Yeah, 1.2. I don't need to do an adjustment there. Don't forget the squared. I should be able to backspace again. 15. So I'm going to replace the 08 with a 1.5. And 1.2. That should work. I got 93,750. Or am I wrong? Newtons per coulomb. Direction. Left? Oh, this one's left? That's which way a positive would want to move if it could. Who's winning? I think the rights are. So I'm going to go right plus right minus left. Yes? 112,500 plus 44,953 minus answer button. The net electric field at that location is 63,703. So 63,700. Units, newtons per coulomb. Direction. Right? Right. So to summarize, we can find the electric field by using the definition if we're told the force in newtons, Hannah, and if we're told the magnitude of the charge. Electric field is the force per coulomb, the electric force per coulomb. When do I use that? If they say find the electric field and they give me a force. By the way, that also means that's the mg version of electrostatics. In the same way, F G equals M, G, F, E equals Q, E. It's the same version, the shorter version of electric force. We can also find it using the point charge equation if we're told the magnitude of the charge that's creating the electric field and how far away we are from it. Recall, electric field direction is found by considering a positive test charge. Which way would a positive want to move if it could? Why did we have to have a direction? Because stuff can fall up. Force can be found using Coulomb's law if we know both charges and their separation distance. But the shorter version, if you happen to know the charge at that field point and you happen to know the electric field at that field point, that's the mg, get the obvious one, short version of electrostatics. Direction of electric force is by like charges, unlike charges attract. Their force and field are vectors. If we have multiple charges, we'll need to add them vectorially by going win or minus. I'm going to say homework, try number 3. Try number 4. Try number 5. 6 is good. $11 is good. $13, $17. And I need to do 2 things. I need to show you Wingardium Leviosa, and I need to show you an addictive video game.